Hello everyone, I'm making another video tutorial to provide you some hints on assignment number 9. I think it was pretty well received for assignment number 8, so we're going to do the same thing. So some of you tutorial on Friday, and so these hints will be able to help you instead of wait until Friday. So let's take a look at problem number 1. Okay, so for part 1a, what I want you to really do is not just simply look at a table and provide the answer. That's really kind of too simple. So for the A here, what I really wanted you to do is actually, because you have a cosine function here, okay, and I want you to expand this one using a trig identity. Okay, so you expand it, and and then you take Laplace transform of both sides. Okay, so if I take Laplace transform of this side, essentially it's equivalent. Okay, taking Laplace transform, and the cosine theta, sine theta, you consider them as constant, so you can take it out of the Laplace transform. Okay. Okay. So now you can use table to fill out the blank here. So from the table you have Laplace transform for cosine omega t, and you have Laplace transform for sine omega t, and just put it here, and then do some simplifications. You'll be able to get Laplace transform for this one here. Okay, so that's part B, part A. So for part B, okay, it's basically a special case of A, and nothing much. You can do what you have done over here, or you can just simply plug in the formula, and that's fine with me. Now, so for part C, this is a part you need to make use of Laplace properties. So let's take a look at this one here. The function has two parts. Okay, so Laplace transform of f of t, okay, is Laplace transform of 2t u of t, okay, and Laplace transform 5 e to the negative 3t minus 2 and ut minus 2. Okay, and the first Laplace transform is very easy. You can take a look at your table. Okay, now I need to mention this in the table. Let's go back to see if I have it here. Okay, here. Now in the table, what I need you to point out here is, I said all the function I'm considering is a causal function. Okay, it's basically a causal here. So I don't have f of t multiplied u of t here, but essentially it's just f of t multiplied by u of t. Okay, so if example, in this specific case here, I have this Laplace transform of t. Essentially, it's just same as Laplace transform of t u of t. Okay, so that's why I'm neglecting u of t here, because everything is considered as the causal signal here. So that's why the first Laplace transform here is 1 over s squared. Okay, so what about the second Laplace transform? Now this one here will make use of this property over here. Okay, the properties. The properties over here, and this property. Okay, so we have f of t minus capital T, u of t minus capital T, and its Laplace transform of this whole thing is e to the power negative s capital T multiplied by capital F of s. And capital F of s is the Laplace transform of f of t. Okay, so let's go back to here. Okay, so when I look at this one here, well, this is t minus 2, this t minus 2, it matched perfectly of the property over there, right? So the only problem is, so what is f of t here, right? And f of t here, you look at this one here, it's basically e to the power negative 3t, okay, for this one, okay, and there's a u of t, okay. And the Laplace transform of this one is capital F of s, 1 over s plus 3. Okay, so now you probably know, okay, the inverse Laplace transform, the Laplace transform of this whole thing, okay, is 5 according to my property, okay, property over here, okay, is e to the power of negative s, capital T here is 2, okay, and then capital F of s is 1 over s plus 3, or is basically 5 e to the power of negative 2s, 1 over s plus 3, right? So that's part C. Okay, for part D, for part D here, you basically just have to use the hint for coach for t, okay, and then make use of table for exponentials you'll be able to. For part D, okay, for part D here, okay, let's look at part D. The function is f of t equal to 2e negative 4t u of t minus 1. Now when you look at this one here, the objective is we still want to use that shifting property, okay, the shifting property. So the shifting property here is f of t capital T and u t capital T and e negative capital F f s capital f of s. Okay, so we still make use, but the only problem here is, so let me rewrite this one here. The only problem here is this function is e 4t ut minus 1. So if you compare here and here, okay, so this is good, right? To match it up. So basically I can have the capital T equal to 1, right? But here I don't have function of t minus 1 or t minus capital T here. So what do I have to do? Okay, can I change this to t minus 1? Okay, I want to change it. If I can change this, then I can make use of the property, right? Well, but you changed it, but you cannot change the original function, right? So we have to do something to make sure we're not changing this original function. So what do I have to do? Then I have to multiply e to the power of negative 4, so that I won't change the original. Now you might want, oh, where's this from? Well, you look at this guy here, right? This is e to the power of negative 4t plus 4. Okay, so this is where your negative e to the power of negative 4 is from. Okay, so you are not changing the original function here. Okay, now you're ready. You can take e to the power of negative 4. You consider that as a constant. Okay, so the Laplace transform of 2 e negative 4 e 4 t minus 1 u t minus 1. Okay, and which according to my property here, okay, is e to the power of negative s. Okay, what t is capital T is 1, so 1, and capital F of s, right? The f of t is e to the power of negative 4t, so that's 1 over s plus 4. Okay, so that's basically what you get over here. Okay, yeah. Okay, so that's part 1. Okay, that's problem number 1. For problem number 2, okay, this is a simple question, and you just make use of the initial value theorem and the final value theorem right here. Okay, basically calculate the two limits. Okay, and then you get your initial and final value. Okay, and the second part is verify it by using partial fraction. So basically you're going to have to take partial fraction of this function here. The denominator contains two simple poles. Okay, so simple format. Okay, so your capital F of s is going to be able to factored into two parts. Okay, right, it's going to be able to factor into two parts, and you can basically go ahead and then try to solve for a value of a and a b, and then take an inverse Laplace, you get a time function. Okay, then you'll be able to verify it. Okay. As a matter of fact, you can just change this. Just use a and b, okay? Because this really doesn't matter because you can compare that, okay? Yeah. So that's problem number 2. If you use that, I think what you're gonna get for a and b, you compare coefficient for a, you will get negative 5, and b you are gonna get as 10 over here. Okay, yeah. So problem 2, and let's see problem 3. Okay, so problem 3 is determine inverse Laplace transform of each one of the following functions. This is another exercise of using partial fractions. Okay, so partial fraction, for part A, you just have to be able to tell. You look at the denominator. And the denominator here is have 3 simple poles. Okay, so your original s function, okay, should be able to rewritten as a partial fraction term, okay, as a over s plus b over s plus 2, c over s plus 4. Okay, then you compare coefficient, or you can use the formula as we did, right? A is s, okay, multiplied by capital F of s, or just basically this whole thing here, okay, and let s equal to 0, okay, which is 8. You get 3. Okay, so you can do similar things for b and c. Okay, you can find b is 2, c is 3. Okay, so let's see. Yeah, you get that. Hopefully, that should be right. Okay. So for part B, it's the same procedure, but except that the denominator, okay, except the denominator is a little bit different. So look at the denominator. This is s plus 3. This is s squared plus 4. So there is a second order here. Okay, the second order. The second order term here, s squared plus 4s plus 5, as you're gonna find here, is you have a complex conjugate roots. Okay, so this term here, you should be able to rewrite. Okay, you should be able to rewrite it as a over s plus 3 and bs plus c over s squared plus 4s plus 5. Okay, so that's how you're gonna get, and then you go ahead and compare coefficients to solve for a, b, c. Right, so this side numerator is s squared plus 1, and the other side the numerator is a s squared plus 4s plus 5 plus bs plus c s plus 3 equal to s squared plus 1, right? So, okay, compare coefficient, group all the terms for s squared and s, solve for a and b. Okay, solve for a and b. So once you solve for a and b, okay, and what you're gonna get is the a value. I think what you're gonna get is 5, and b value, what you're gonna get is -4. C, you're gonna get this. Okay. So try to solve it. Okay, don't just write it down on your assignments without showing any steps right here. Okay. Okay, so I think the next thing is you need to manipulate this term so that you can make use of the Laplace transform by looking at the table. Okay, so you basically, let's see here, this becomes 4s minus 8 s squared plus 4s plus 5. Okay, and you take a negative sign to your -4 out. Okay, this top one becomes s plus 2, and bottom one here is, you can change that to s plus 2 squared, okay, plus 1. Okay, so you get this one here and actually match exactly what you have for the Laplace table, which you get e to the power of -2t cosine t. Okay, so your omega is 1 here. Okay, so now you should be able to solve for this one here. Problem number 4. Okay, problem number 4 here is using the Laplace transform to solve convolution. This is nothing tricky at all, actually. Basically, you make use of the property. Okay, so f of t, well, here's h of t. So let's see. So h of t convolute x of t. Okay, and the Laplace transform this guy is capital H of s multiplied by capital X of s. Okay, so obtain the H of s and X of s from here and here by looking at the table. Okay, and delta of t's Laplace transform is 1, and then you do inverse Laplace. So basically what you're going to get for this guy here is 4s over s plus 2 s plus 3. Okay, now you want to do inverse Laplace transform, then you have to use partial fraction. Okay, so then try to solve this guy, this one here. Try to solve a and b. Okay, So your A and B will be solved as this. Okay, now you take Laplace, inverse Laplace, and you get the convolution. Okay. So for problem number 5, this is a typical application of Laplace transform in solving differential equation. And I put this one as one of the tutorial question. The first step, of course, you need to take Laplace transform both sides of this differential equation. Okay, and don't forget to use the differential property. Okay, right, and before you get the right result. So this is s here, and y prime of 0, okay, plus 2 s capital Y of s, okay, and minus y of 0. Okay, and the last one here is 10 capital Y of s. Okay, and the other side is 3 cosine 2t is 3s over s squared plus 4. Okay, so that's basically this. Substitute the initial conditions here and here. Okay, and solve for capital Y of s. Okay, so your capital Y of s should be solved, and what you're gonna get here is s cubed plus 7s, okay, over s squared plus 2s plus 10 s squared plus 4, like this. Okay, so from here, partial fractions, okay, expansion and decomposition. So what you're gonna get here is, because there's this second order term which you have a complex roots, okay, so you should be able to expand it like this. Okay, so this is s squared plus 4, and that's also a term with 2 complex roots, so cs plus d s squared plus 4. Okay, so that's what you can hold. And then compare coefficient and solve for a and b, c, d. Okay, this is fairly complicated, and you need to be careful by solving this. So what you're going to solve is okay, this is what you're gonna get. Okay, so be really careful here. Okay, and the last step, when you plug A, B, C, D back over here, you have to manipulate these 2 terms, okay, in order to match your table from Laplace transformation. Okay, so there's quite a bit of factorization here. So let me show you maybe one example here. Let's see. This first term there. Okay, so that's the first term here, and I'm what the bottom one here, I can rewrite it as s plus 1 to the power square, okay, and plus 9, which is, and plus 3 squared, okay, plus 3 squared. So the top one here, and I really wanted to match the sine and cosine things, right? So what I can do is I can do this. So 17 over 26s plus 17 over 26, you know, so that I can take the 17 over 26, make it s plus 1, so then, you know, make this thing here. But then I have to minus 17 over 26, right, and plus, okay, and minus 30 over 26. Right, that's what you're gonna get. So for this term here, 17 over 26 s plus 1. Okay, and the other term here, 17 over 26, 30 over 26, that's 47 over 26. Okay, so I can separate this term into 2 parts. Okay, so that's 47 over 26, and 1 over s plus 1 squared plus 3 squared. Okay, there. And so now if you take the inverse Laplace transform this term, and then you'll be able to get it because you already have that the format in your table. But only part of this term here, right? In term here, what you have here in the Laplace transformation table is a little bit different. So we have to do one more little manipulation there. So 47 over 26. I need to change the 1 to 3. Okay. And if I change this 1 to 3, so I have to multiply by 1 over 3. Okay. So that basically now you're ready to take the inverse Laplace transform. Okay. The inverse Laplace transform. Okay. From here is equal to 17 over 26. And this term here is a cosine term, so e to the power negative t, that's coming from this plus 1 here, okay, cosine 3t. And this whole chunk over here, that's 47 over 78. Okay. And this is a sine term, right? It's a sine term here. So that's basically e to the power of negative t sine 3t. There, so that's how you're gonna, okay, you can do similar things for this term over here, okay? Alright, so let's take a look at the problem number 6. Okay. Yeah, actually this term here, just a second, this term here has nothing to do with exponential. Now you can take a look at your Laplace transform. It's just going to be cosine 2t and sine 2t with different gains. Okay. So problem number 6. The only problem here, this is an integration term. So integration term, which means when you take Laplace transform both sides, and what you're gonna get actually, you're gonna get. So when you take Laplace transform both sides, the first term you're gonna get is s capital Y of s, and minus y of 0. Okay, minus y of 0, and we have the initial engineer. And the second one here, what is the Laplace transform of integration? Okay, now you do have such kind of thing in your table. Okay, and what you get here is capital Y of s over s. Okay, and you don't have to care about the initial condition here. So the other side here is s over s squared plus 4. Okay. There, so that's basically what you're gonna get, and group all the terms regarding y of s and get an expression for capital Y of s. Okay, so what you're gonna get, the expression for this one here is s cubed plus s squared plus 4s over s squared plus 4, s squared plus 9. Okay, there, I got two terms on the numerator and the denominator, and both of them are containing complex conjugate roots. Okay, so then I can separate, I can do partial fraction like this. Okay, like this. Okay. So then by comparing coefficient, solve for a, b, c, d. Okay, so you get a 0, and b is negative 4 over 5. C is 1 and D is 9 over 5. Okay, yeah, please really do it, and just don't write this in your assignments. Okay, so now substitute in the back and do inverse Laplace, and you'll be able to get the answer just as I listed over here. Okay, so that's all the hints I can provide for these assignments, and let me know if you have any questions. Thank you.